Hello everyone, it's an honor to share our work with you. At the 51st International Conference on Parallel Processing, our theme is Parallel Network Slicing for Multi-ASP Services. Our showing content will start from 5 parts, which are the research background, the challenges of this problem, the method proposed in this paper, the experimental results, and the conclusions. Firstly, let's start with the research background. In order to support this research, parallel network slicing for multi-ASP services, we refer to the network slicing framework proposed by the European Telecommunications Standards Institute. This framework introduces the management object of network slicing, the function of each object, and the specific workflow. First, tenants prepare service profiles describing their designed network slicing and submit it to the SPs, including some service requirements. Through building algorithm, SPs generate network slicing deployment policies for tenants, in combination with the service requirements and available network resources. The NOP receives the deployment policies and instantiates the slicings. Eventually, these network slicing are delivered to the tenant. We analyze some challenges of parallel slicing deployment. There are 3 main difficulties in solving this problem. Firstly, as SPs can respond to their tenants in parallel for various services, resource competition or even conflict between multi-SPs is inevitable, which reduces the resource utilization efficiency of edge networks. Besides, existing methods expose deployment policies to each other when coordinating multiple SPs and processing network slicing requests in parallel, which exposes the privacy of tenants. The last one is neural network models with fixed input require retraining or re-architecture due to the dynamic changes of edge networks, which increases the difficulty of application. In this section, we describe our method in detail. In view of the 3 challenges in previous parts, we propose 2 main innovations in this research work. We propose ComDI to deal with the first challenges, and the neural hot blocking learning is to deal with the dynamic changes of the network. We consider 2 objective functions. The first is to maximize the acceptance rate of network slicing requests. We specifically describe the acceptance and resource conflicts of network slicing in the paper. The second is to minimize the consumption of bandwidth resources, because the node resources are fixed, while the link resources are diverse during the deployment of network slicing. We use multi-agent deep reinforcement learning algorithm in this work, and the designer of agent use MADIL algorithm is a very important part. There are three main aspects to designing an agent: state, action, and reward function. In this case, our station space includes network state and slicing request information. The network state contains all available resource capacity, and the slicing request information is the inflow point, outflow point, and resource requirement. The action space is a set of network nodes, and each action corresponds to the deployment of a virtual network function. Also, we split the reward function into two parts. The first is node selection, and the proportion of available resources of the selected node is used as feedback, followed by the path selection. The selection of node will affect the mapping of paths. The first part of the reward function is the length of the shortest path, and the later part is the length of the current mapping path. The purpose is to get the agent to reduce the consumption of bandwidth resources when deploying network slicing. The final reward function is the weighted sum of the above two parts. We adopt a sequential decision approach to generate deployment policies for network slicing. Agent deploys the virtual net function in sequence according to the predefined sequence of the network slicing. After all virtual network functions are deployed, the agent calculates the slicing mapping path. The two are combined to generate a slicing deployment policy. The deployment of each virtual network function is the action of the agent, and the reward value of this action will be calculated to evaluate the pros and cons of the action and train the agent. This section introduces the ComDL, which is proposed to realize resource coordination when multiple SPs deploy network slicing in parallel and improve the utilization efficiency of network resources. The slicing request deployment policies of multiple SPs are submitted to the NOP to request network resources and slicing instantiation. The NOP summarizes the deployment policies of all SPs, calculates the sum of the network resources required by the SPs, and compares it with the available resources of node and link in the agent network. If the resource conflict is found, and the resource of a node or link is not enough to support requests from multiple SPs, a deployment feedback is sent to the SPs with resource conflicts. SPs receive deployment feedback from the NOP and correspond the received communication information with their own deployment policies. The reward value of the actions are modified, which are the conflicting nodes. Finally, these experiences are stored and used to train the model. In this process, each service provider, which is also an agent, does not communicate with each other directly, and the communication information is only the information of its own conflicting nodes, so the privacy of the tenant can be guaranteed. To adjust the dynamic chains of edge networks, we propose neurons hot blocking learning to extend the standard MADL algorithm. We demonstrate the method by using the network structure of Dezhi. In the structure of network chains, it means that the dimension of state and action space chains. At this point, we insert or unplug the neurons corresponding to the input and output layers. The new parameters are replaced by the redundant parameters. The other parameters are directly inherited from the old model. In this way, we collected data in the new network environment to train the new model. After introducing the proposed method, we started to present the experimental part. The first point is our experimental platform. The whole simulation system is implemented with Python. All experiments are done into real networks. INS-IXE services contain 33 nodes and the IRIS networks contains 51 nodes, all from the top zone. Other main parameters such as the parameters of the edge network and the model can be seen in our paper. Into real networks, we test two key metrics by changing the upper limit of network resource capacity. One is the request acceptance rate, and the other is the resource conflict rate. As the network resource capacity rises, the performance of each algorithm improves. In these two metrics, ComDL has taken the best performance. Moreover, the advantage is more obvious when the network resources are short, which is also in line with the resource situation of the edge network. The slicing request acceptance rate is increased by 7.9%, and the resource conflict rate is reduced by 14.5%. The difference between the algorithm Dezhi and ComDL is that Dezhi does not join agent communication. Therefore, from the experimental result, we can see that our method is effective. These four figures show two other metrics, which are the bandwidth resources consumption and communication overhead. The bandwidth resource consumption of the proposal is similar to the algorithm CDF-SAPGA. This shows that our reward function can guide the agent to make effective decisions. However, CDF-SAPGA is an exponential complexity algorithm with high solution time cost, because it's a method of traversing the solution space to find the optimal solution. While our algorithm is polynomial complexity, the bandwidth resource consumption of eigen decomposition is more in times that of our algorithm, and the excessive consumption of linked resources also makes it perform poorly in acceptance rate and resource conflict rate. Communication overhead is the cost generated by the multi-agent communication mechanism. As a result, our method improves the network performance at a low cost. This result demonstrates the performance of neural hot plugging learning. We test the performance of the proposed method by changing the network structure of INSXC services, adding or removing some network nodes to simulate the network dynamic. It can be seen that our method reduces the training time of new models by at least 80% and improves the adaptability to dynamic networks. Finally is the conclusions. Our work has 3 main points. First one, the resource conflict problem is explored when multiple service providers deploy network slicing in parallel in the resource sharing edge cloud. To solve the resource conflict, ComDIA with MADIA and multi-agent communication is designed to coordinate the resource requirements of multiple SPs. The proposed neural hot plugging learning makes MADIL algorithm more extensible. In the future work, we will attempt larger scale network and apply neural hot plugging learning to different neural network architectures. Thank you for your listening. This is the end of my sharing.